Hi everyone, I'm Xu from UC San Diego. Today we'll be looking at a type of deformation called surface fractures near the ridgecrest area. Here are my collaborators for this study. Before we get into today's talk, here is a short outline. We'll go through some tectonic settings, observations we made, our modeling, analysis, and some interpretation. In the end, I'll wrap up with some conclusions. Here is a tectonic map for the region I'll be talking about today. It is largely located in the Mojave Desert, in between the Walker-Lane Belt and the Eastern California shear zone. Here's the Garlock and here's the San Andreas Fault, and here is the coastal geothermal field. The rupture roughly lies between Garlock and the coastal. These white segments denote historic earthquakes: the 1872 Owens Valley earthquake, the 1992 Landers, and the 1999 Hector mine. Okay, right-hand side is the regional map that shows the Sentinel-1 satellite car ridge. It is very well mapped by the two log directions of data. The red box denotes the area of rupture, shown by the left two interferograms. One could unwrap these interferograms to derive the coseismic deformation field. Due to the existence of unwrapping errors, especially when it comes close to the fault, if one tries to look for small-scale features surrounding the rupture, assistance from a different technique is needed. And the technique is phase gradient mapping. Phase is a matter of distance, thus phase gradient is essentially measuring strain. The pros for this method is, first, there's no need to unwrap the phase, as phase gradient could be derived by combining the gradient on real and imaginary parts of the SLC. And by doing that, you are able to bring up the details in the map. And because you don't have to unwrap the phase, you can directly stack them to reduce noise. And the cons are, when you are taking the derivative, you are essentially magnifying noise. And because it's magnifying noise, any type of decorrelation will be a big problem. This is why when we are computing phase gradient, we're combining a derivative and Gaussian filter. But still, when you are looking at the map on the right, it is a bit noisy. And 20 years later, we have Sentinel-1, where data are much improved. So what are we seeing in this map? Since phase gradient is measuring strain, any line in this map that shows a strong contrast is indicating strain localization. And we call them the surface fractures. Note that these very straight lines are burst boundaries, not really surface fractures. The phase gradient map could tell where the location of the strain localizations are, but to understand what really happened to them, one has to go back and check the phase. So we stacked unwrapped deformation field, decomposed them into largely east-west and up-down directions, and high-pass filtered them. Note for these two maps, positive is east and up. For example, this fracture here, red is on top of blue, so this fracture has a right lateral deformation. At this scale, things are a bit messy, so let's zoom into this southern section. The fault has blue on top of red, so foreshock is left lateral. However, when you look at a number of these fractures, they are actually deforming right laterally, which are opposite to the rupture. And associated with these fractures, some level of subsidence was also discovered. Normally, if an earthquake happens, it usually goes along the direction of tectonic stress. For example, here, surrounding the ridge crest, the inferred SH max is largely north-south. That indicates if the fault goes along the 7.1 rupture, it should be right lateral. If it's more aligned with the 6.4 rupture, it should be left lateral. Here we define for these fractures, if the measured deformation goes in the expected direction from the background tectonic stress, we call them prograde fractures. If they go the opposite direction, we call them retrograde fractures. If you map all the fractures on surface, here's the map of how they look like. At first look, there are a few prominent transitions, like these fractures to the northeast, and these to the south. The retrograding ones could not be explained by the tectonic stress, and thus other sources are needed. And of course, the biggest source here is the ridgecrest earthquakes. So we inverted for a kinematic slip model using a compilation of data, and used it to compute surface stress along the directions of these surface fractures. We tuned the regional tectonic stress to find the best match, where a smaller number is going to feel the transition to the north, and a larger number will feel the transition to the south. We could largely conclude that these motion we saw on these fractures could be well explained by the stress release from these two earthquakes. The remaining question is what mechanism? Are these retrograding fractures really fault slips that go backwards? Usually people would believe that the earthquake stress release should be no larger than the accumulated tectonic stress. So how do we explain these ones that go backwards? If we try to explain everything with frictional slip, there are a few questions that are hard to answer. First is that if you do a profile analysis for some of these surface fractures, it will show some slip did not reach up to surface. In other words, deformation across the fault are not really a sharp step. The second is these subsidence along the faults. When the fault is frictionally sliding, why are they going down? Did they collapse and fell? So other than frictional sliding, there is another explanation called compliant fault deformation proposed by Fialco et al. 2002. Compared to what frictional sliding predicts, where fault under excessive stress will slide with the fault plane that breaks in the middle, the compliant fault deformation does not require the fault to break. In other words, with extra stress being applied, generally the crust will deform. And because surrounding the fault plane, there is this well-known fault damage zone where shear modulus is much smaller than the surrounding hosting crust, thus that the fault damage zone will deform more than the surrounding material and cause strain localization. Also, since it did not break in the middle, the fault remains as a continuum and could respond to compression or extension. Thus, you will be able to see the upward or downward motion. To better understand what mechanism these fractures belong to, we did profile analysis on every segment of these fractures. So we take profiles, stack to reduce noise, and then measure the displacement amplitude and the deformation width. Then with the computed shear stress, we could compute the shear modulus ratio. In other words, the ratio of shear modulus in and outside the fault damage zone. What is shown here is an example. After you do all these analyses, here are the histograms of these parameters. The yellow color denotes histograms for all fractures, and the pink is for prograding and the blue for retrograding. And from top to bottom are deformation width, displacement amplitude, and the shear modulus contrast. So for the displacement, prograding and retrograding do not show much of a difference, but the retrograding fractures seem to generate systematically wider deformation, and thus created shear modulus ratios that physically make more sense, largely from 0.4 to 0.8. This range of numbers makes sense, and seismic tomography have found similar amount of reduction in shear wave velocity near faults. For frictional slip, the deformation over width term will be much larger and lead to very small and unreasonable shear modulus ratios. From these analyses, it seems that the prograding fractures are likely to be frictional slip, while the retrograding fractures are likely to be compliant fault deformation. To explain that, we made this conceptual model called critically stressed fault. Initially, everything is reset, for example, after a big earthquake or something similar. With tectonic loading, the fault will get into a status where it is on the verge of breaking into a frictional slip. And with a tiny bit of extra stress, it will. However, this frictional slip does not fully release what is accumulated here. It only partially let go of the stress. Then the fault comes back to this critically stressed status. Naturally, just from tectonic loading, the shallow fault will go in this cycle, consistent with what is observed as the episodic nature of fault creep. Since the fault is almost always in this status, when there is an earthquake nearby and impose extra stress to the fault, if the stress goes along the direction of tectonic stress, it'll be frictional slip. If the stress from the earthquake goes against the direction of tectonic stress, in fact, it'll bring the fault away from failure and thus cause compliant fault deformation. So to explain what we observed, the key is to have this buffer. In other words, to produce a backward-going frictional slip, you have to overcome this buffer first, which is almost impossible. Note that this critically stressed status is also controlled by a number of parameters, like fault friction, normal stress, cohesion of the material, and so on. It also explains sometimes when strong dynamic wave passes by and causes this status to drop, it'll let go a very strong creep event to release what's stored in this buffer. In the upcoming years, the fault will be basically compensating what's released and no creep will be observed, which is called a stress shadow. This is essentially what happened to the Southern San Andreas fault after the Elmira-Cucaba earthquake. Here are some evidences for the model. The northern part of the region, you have a stress transition over here. The nearest one, it might be a bit hard to see, is left lateral motion, with quite strong subsidence in the middle. The furthest one is right lateral motion and almost no vertical deformation. And the one in the middle is really interesting. The stress is slightly promoting right lateral slip, but it was able to hold for most part until it reaches the right end where stress is larger. And when you look at the vertical, it's subsiding on the western part. It continued until you see this right lateral motion. So this segment is a case where the imposed stress is low and it did not evolve into frictional slip, but it's getting really close. Now let's see what we could get from this study. First and foremost, we found a lot of new faults. Frictional slip in its mechanism could be either new ground cracks or shallow fault creep, but compliant fault deformation do require pre-existing faults with fault damage zones. Essentially, this technique is giving us a tool to map faults from space, especially those bland ones or at low strain rate area. And of course, this couldn't be done without Sentinel-1 satellites. Also, we believe these types of fractures may exist in many other diffuse strike-slip fault systems, like the recent 6.5 Monte Cristo Range earthquake, where you could even find a shallow post-seismic fracture. However, most of them, when you look at the decomposed map, are prograding. This could be due to this area is inside Walker Lane belt and is under transtensional stress. Another example is the 2017 Iran-Iraq earthquake, which is the thrust event. Over the epicentral area, again, a lot of surface fractures are discovered. You could find some really prominent ones like this one, and over here, and over here. The red lines are previously marked faults. If you zoom into this area, things are becoming really interesting. There is this flow-like texture all over the place. Most of them are only a couple of 100 meters away from each other. When you look at the topography, there might be something there, but are far less sharp. Also, how do we define pro and retrograding for a thrust event like this? What are we essentially seeing here? More of these cases needs to be looked into to help us understand what's going on at Earth's surface. There are some interesting characteristics you could derive from the observations of these faults. But firstly, these faults must be very young, or to be more exact, immature. If the fault displacement and length scaling applies to our scenario, most of the faults we observed is a few to tens of kilometers long. Thus, the historic slip will be 10 to 100 meters. Also, Savage and Brodsky found this relation between total fault slip and fault damage zone width, where 100-meter total slip will produce roughly 100-meter wide fault damage zone. Thus, surrounding the ridgecrest rupture, these faults are quite immature. Another aspect one could derive is how deep that these faults go. Here's a simulation study by Ampure and Mall in 2017, where they verified the relation between fault damage zone width and seismogenic depth. A smaller seismogenic depth will produce a narrow fault damage zone. Based on this relation, we would expect all the discovered faults here are less than 5 kilometers deep. So most of the observed new faults are associated with very shallow structures. The final implication I'd like to get into is the shallow slip deficit. Normally, there are two hypotheses to help explain this shallow slip deficit. First is shallow slip occurs on the shallow part of the fault at other times in the earthquake cycle. Second is shallow slip is taken up on other distributed structures. What we observed here is a direct support to hypothesis 2. But of course, finding evidence for one does not deny the existence of the other. Also, we summarized all deformation associated with these fractures, and their total is less than 4% for both pro and retrograding fractures. So these faults are not taking account for the SSD co-seismically. Based on the conceptual model, these faults either release strain aseismically over the interseismic period, or they could be taking turns to produce smaller events. However, this area is with very low strain rate. We did stack a large number of interseismic phase gradient maps, but none of them showed any strain localization. So I'm wondering whether the latter is the real case. Here are some conclusions. We found a lot of unmapped faults near the ridgecrest area. With the relations between fault damage, length, displacement we discussed, this might be providing us a new way of mapping faults. For these observed surface fractures, some of them are going in the direction opposite to the prevailing tectonic stress. The mechanism for pro and retrograding displacement are different. The prograding ones are likely to be frictional slip, and the retrograding ones are likely to be compliant fault deformation. These faults we documented are in situ records that immature faults also have well-established fault damage zones. And the distributed fractures may account for the larger SSD derived for the 2019 ridgecrest earthquakes. Thanks for listening.